For our last section on integral techniques, we'll be talking about what we call improper integrals. Improper integrals are going to be integrals that involve infinity in some shape or form. And since infinity is not a real number, that's why we call them improper as opposed to proper. So the first thing that we deal with here in improper integrals is talking about infinite intervals. So looking at this picture here, we have a function and we're starting at some a value and we're looking at integrating, and we're integrating to b, but we're looking at what happens as b goes off to infinity. So essentially what's happening is we're seeing that our function value is getting closer and closer and closer to 0, and we're wondering if when we keep taking chunks of area, will the chunks get small enough that this whole area will eventually collapse down into a number. So if we're looking at a continuous function on a to infinity, then we can look at the integral from a to infinity of our function as being this limit here. So we're going to replace the infinity with b and just take the limit as b tends to infinity instead, because that's going to be mathematically proper for us. And this is only true provided the limit exists. If the limit doesn't exist, then we'd say that this guy diverges. Likewise, we can go the opposite direction as well. We can go to negative infinity, and we would replace the negative infinity with some other variable, and we will take the limit as that variable goes to negative infinity. So we can integrate either to infinity or negative infinity using limits. We can also do both at the same time. So if we go to from negative infinity all the way up to infinity, then what we'll have to actually do is we'll have to pick some c value that's just kind of in between a and b. Really just usually 0 is going to be our best bet, since that's kind of halfway between, quote unquote. Then what we'll do is we'll split it into an integral of the right side, so from c to infinity, and we'll apply the same limit there. And we'll have the integral on the left side from negative infinity up to c. We'll replace negative infinity with a, and it'll act just like this upper situation here. As with any of these, if the improper integral has that limit value that does exist, we'll say it converges. If it doesn't exist, either by oscillating, by blowing up to infinity, or by going down to negative infinity, something like that, then we'll say that the integral diverges. And we'll be using the words converge and diverge a lot in the next unit as well. All right. So again, things to look out for. Oscillating integral values. If the integral converges to kind of two values at once, then remember that doesn't converge. The limit has to just go to a single value, and then going to either infinity or negative infinity. So we'll go ahead and take a look at an example here. First we have 0 to infinity, we have e to the negative 3x. So again, it's all about, does this function sort of collapse down to 0 fast enough so that when we integrate out to infinity, our area added gets smaller and smaller. All right, so we'll go ahead and take a look then. The first thing we do, whenever we see that we have a limit or an integral that's got infinity on it, is we want to replace that infinity with a letter and use a limit to convey that idea. And the typical usage is, if it's infinity, we'll replace it with b. If it's negative infinity, we'll replace it with a. That's not that important. You can kind of pick which letter you want, just as long as it's not like x or a letter that's already present in the problem. So we'll go ahead and integrate here. We've got the limit as b tends to infinity. And this one is not very difficult, right? It's an exponential, so its integral is itself, but we have a chain rule to overcome here, so we'll divide by the coefficient. And so we're evaluating this from 0 to b. Right, probably best to take that negative 3 in the denominator and actually bring it outside. We can bring it outside of the integral, and since it's a constant, we can also bring it outside of the limit itself. And so we'll go ahead and do that, and we just get e to the negative 3x here, evaluate from 0 to b. Right, so we have negative 1/3, and we'll go ahead and evaluate the integral. So we have e to the negative 3b minus e to the negative 3 times 0. And so when we do that, we get, oops, negative 3 times 0. So we get e to the 0 there. That's going to be just 1. So we get the limit as b tends to infinity here of e to the negative 3b minus 1. And so this is the same thing as negative 1/3 times the limit as b tends to infinity of 1 over e to the 3b minus 1. And so as b tends to infinity, this guy will go to infinity in the denominator, and so this entire fraction itself will go to 0. You can basically just go straight from here to here. I'm going to expect us to have a pretty commanding knowledge of limits at this point, so we should be able to just skip straight from one to the next. So in the end, we get negative 1/3 times, we've evaluated this limit now to be negative 1, so we get positive 1/3. So that's going to be our limit value. So that's our integral value. Our improper integral converges to 1/3. So since we got a numerical value, this converges. So as it says here, the limit exists, so the integral converges. The region under the curve has a finite area. And the idea, again, is looking at the function here, is that it gets smaller and smaller and smaller, closer and closer to 0. So even though we're adding an infinite sort of amount of area here, an infinite length on which to do area, the actual area that we're adding essentially collapses to 0. And so we end up getting a finite value here of 1/3. All right, as another example, we see this guy here. Kind of a spoiler, it shows us what value we should be getting, but we'll go ahead and take a look at how we get something like that. All right, so again, if you see infinity in an integral, your first step should be to replace that infinity with some letter and then make a limit as that letter goes to infinity instead. And so with that, we now have the ability to evaluate this integral. We keep the limit there. This is the exact derivative of the inverse tangent of x, or the arctangent of x. And we'll go ahead and evaluate this from 0 to b. So we get the limit as b tends to infinity of the inverse tangent of b minus the inverse tangent of 0. And just so that we remember what the inverse tangent looks like, it looks like this guy. We have horizontal asymptotes at pi halves and negative pi halves. So if we look at b going to infinity, then we're looking at this right end behavior. We're looking at a value of pi halves. Meanwhile, the value at 0 is 0. Our inverse tangent goes to the origin. And so we're looking at just a value of pi halves. So this one converges as well. All right, so that's the basic idea then of improper integrals that involve infinity in the limits. So it is just going to be making a limit as the letter goes to infinity, and then a regular integration. So we're just basically adding a limit evaluation on top of our integral evaluation. But as you can see here, we can also combine our limits at infinity in our integrals with the solids of revolution. So we have a region bounded by the graph of y equals x to the negative first and the x-axis, and it just says for x greater than or equal to 1. So we can see here in the picture, we've got 1. We're actually going to go all the way to infinity from there. And we're going to be doing a volume of a solid when r is revolved about the x-axis. And so when we're dealing with something like this, especially when we start talking about improper integrals, we're not going to want to swap, are we doing this in y, are we doing this in x? We're pretty much going to want to go with the way that the problem gives it to us, unless there's a clear reason to do otherwise. Maybe the integral actually can't be evaluated or something like that. So in that case, we're going to want to use, since we've got our function in x and we are integrating about the x-axis, revolving about the x-axis, we're going to want to use the disk washer method. So our volume will end up being the integral from 1 to infinity and then it's of pi r squared. R is going to be our function here, so we got x to the negative first squared. And again, first thing we want to do, we see an integral with infinity, replace it with some letter, let that letter go to infinity in a limit. So pi x to the negative second dx. Then pi is a constant, we'll bring it all the way out, not only out of the integral, but out of the limit as well. And then we have just x to the negative second to integrate here. And remember that when we are doing that, we want to use the power rule here, increase the power by 1, divide by the new power. So you have negative x to the negative first. We'll evaluate that from 1 to b. Sorry, should replace the infinity with b. Those didn't make sense. And just so you are aware, it is going to be super important that we don't leave infinities in our integration. We are never going to actually be able to evaluate an integral at infinity. We can only do it using this limit. So having an infinity in your limits of integration beyond this first step won't make sense. So we're going to have to use the limit. Yes, we will have to. So we go ahead and evaluate here. We've got the limit as b tends to infinity. And then in here we have, actually, let's go ahead and take out that negative as well. So I'll make that one more line. So we've got negative pi, the limit as b tends to infinity. X turns into b here, so we got b to the negative first minus 1 to the negative first. b to the negative first goes to 0, right? That's the denominator. The denominator is going to go to infinity, so we get a 0 overall. And so we only end up with negative 1. So we get negative pi times negative 1, which is just pi. And this is a volume, so really we could say that this is cubic units. Not usually necessary though. We'll just go with pi. So we can use these limits to characterize an integral going to infinity even in the application of a solid of revolution. So we'll go ahead and look at another one here. We've got, again, we're looking at the same function and we're looking at the same region, but we're actually going to take that region and revolve it about the y-axis. And again, we're going to want to leave it there as much as possible. So we have a function in x revolved about the y-axis. We're going to have to use the shell method. So we'll do 2 pi x times x to the negative first. And we'll go ahead and take this from, again, 1 to infinity. All right, just real quick, thinking about why we wouldn't want to use the disk washer method here. If we're going to go about the y-axis here, then if we try to make a slice using y, we'd have to make a horizontal slice, and you can see like right about here, we start getting some problems. And so at 0, we'd end up actually having an infinity inside of our integral, not on the, not even on the limits of integration here. It would actually be inside. We'd have a value blowing up, and we don't have the equipment to deal with that right now. So we actually can't do it in this method. We'll have to keep the shell method. And so we'll go ahead and introduce our limit. So we got from 1 to b. And then we've got 2 pi, and then x times x to the negative first. We end up with just 2 pi. All right, we'll go ahead and bring that out. So when we do that, 2 pi, limit as b tends to infinity, we end up with just dx as our integrand. And so we'll get 2 pi, and we'll have to integrate this. We get just x. So x evaluated from 1 to b. So we get 2 pi, limit as b tends to infinity, and then we have b minus 1. But the thing is, b is going to infinity. So when that happens, we end up getting an infinite limit. This does not converge. We'll end up with infinity, which is not a real number. So the volume is infinite. And so we'd say that the integral diverges. All right, so that is a case where our values here don't collapse fast enough because we have sort of this infinite swath that's actually being rotated around the entire axis. It's kind of showing up an infinite number of times, and it's already an infinite distance here. Whereas back in our previous example, we kind of only have this infinite tip on this kind of conical shape. So we will look at also one where we have negative infinity to infinity. This one says set up but do not evaluate. So that's nice. We don't actually have to do the integrals. We just have to show that we can set them up with the proper limits. So when we do something like that, we cannot just sort of introduce two different limits at the same time. What we're actually going to have to do is we're going to have to break up this integral into two pieces. We have to pick some value on their number line to act as sort of the intermediary here. So we'll go from negative infinity to 0, and then we'll also have another integral from 0 to infinity. Right? So if we sort of add these back together, we would end up with the full negative infinity to infinity. But this way we can actually use limits and still be within the confines of our definition. So we'll go ahead and use the limit as a tends to negative infinity to talk about the first integral. And then we'll go ahead and introduce the limit as b tends to infinity for our second, 0 to b. And we could certainly evaluate these integrals, but the question didn't ask us to, so we'll go ahead and leave it that way. Whenever you have a limit from negative infinity to infinity, you must use this process. You must break it up in the middle and go ahead and introduce these limits one at a time. You shouldn't ever have sort of two variables both going to different infinities in the same limit statement, because the question will always be, well, which one do you do first, and why do you do that one first? And so that's why we have to split this up, for consistency's sake. You wouldn't necessarily think that it would make a difference, but there are definitely functions where evaluating the left side first and then the right side would give you a different result, perhaps, than doing the right side then the left side. So we have to split those up. So that pretty much covers what happens when we have infinity in our limits. But now we kind of go back to this previous example and talk about what happens if we have something blowing up in our integrand. And so we'll talk about an unbounded integral. So another version of an improper integral, as it says here, it occurs when the integrand becomes infinite somewhere on the interval. So we look at 1 over root x here, and we look at what happens as c goes to 0. So we see as c goes to 0, our function blows up. We have a vertical asymptote. So as we go to 0 from the right, we have a problem. And so what we'll have to do is we'll have to use this idea that we're going to c from the right, and we'll kind of combine that with the previous strategy here to end up with what we want. So we'll get a definition here. So suppose f is continuous on, and we have an open parenthesis here on a to b. So a is where our problem is. A is where we have a vertical asymptote. It says the limit as x approaches a from the right either is positive or negative infinity. So vertical asymptote at a. So when that happens, we take our integral from a to b, and we'll have to make a limit as some other letter approaches a from the right. We say from the right because we're going from b to a. And so that's what we'll do. We'll again introduce a limit, and we'll sort of swap out the issued area with a different letter and let the limit sort of take care of it. Same thing on the left side. If we have, on the right side, if we have a vertical asymptote on the right side, then we'll swap out our sort of problem area where the vertical asymptote is with a different variable, and we'll let the limit take care of it. We'll let the limit approach our vertical asymptote, in this case, from the left. We can also take an integral that sort of passes through a vertical asymptote. So if we have a to b, and we have some point p where we have an unbounded area or a vertical asymptote, then again, we'll have to split the integral into what's left of the vertical asymptote and what's right of the vertical asymptote. And then we'll have to take a limit as something approaches p from the left for the left integral, and as something approaches p from the right for the right integral. And again, we have the same sort of wording here. If the limit exists, we have convergence. If it does not exist, the integral will diverge. We have divergence. So that's the strategy. And we'll go ahead and take a look at then what happens when we have this sort of issue. So find the area of the region between the graph of, and we have this graph here, and the x-axis on -3 to 3 if it exists. So we do also have that caveat that, these things might not actually exist, and we'll have to be careful. So we'll go ahead and try to figure this out here. Luckily, we look here and see that this function is even. Right? The only power on x here is an even power. Since that is true, we can just look at the right side and multiply it by 2, and then we can get both sides. And so that's the strategy that we'll take here. I'll go ahead and change that to a multiplication sign. Because we have an even function, and because we are evaluating it from -a to a, right? These guys match, they're just opposites. We can actually say that the integral from -3 to 3 of our function is equal to 2 times the integral from 0 to 3 of our function. Be very careful with this. There's only very specific situations where this can work. First off, you have to verify that your function is even. So we'll go ahead and recall how to verify. You plug in -x. And what happens is the square will cancel out that negative. And so we end up with the original function again. And so our function is even. So first, you have to verify the function is even. Second, you do have to have this situation where you're going from -a to a. Actually, you really should check this first, because if this was like -2 to 4, then we wouldn't bother checking to see if it's even, because that wouldn't matter anyway. So check to make sure that you're doing -a to a. Once you establish that, you can see if your function is even. If both of those things are true, you can actually look at 2 times the integral from 0 to a, which in this case is 3. And so that'll be nice for us, because that means that we are only looking at one spot where our function blows up. So we're looking at 2 times, the limit, let's say as b approaches 3 from the left. Remember, whenever you're looking at a situation where you've got an unbounded integral, you do have to worry about, are you approaching from the left or right? It will make a difference. And we'll go ahead and replace our 3 with b. And there we go. So now we have our integral set up in a way that we can actually evaluate it. In fact, I'm actually going to take that 2 out as well. And so we'll go ahead and take a look at this integral. All right, so we can, let's see, do this by a u substitution likely. Let's go ahead and take a look at what we're able to do. This looks very much like the integral of sine inverse. If we take a look at what that derivative is here, then we would get 1 over root 1 minus x squared. So very close. We just have a little bit of an issue here where we have a 9 instead of a 1. So what we'll go ahead and do is a trick that we've probably seen in Calc 1, which is we'll actually take 9 and factor it out. And so we get 1 minus x squared over 9. And since this is multiplication, we can go ahead and we can bring the 9 out of, or sorry, we can split the root. So we have root 9 root 1 minus x squared over 9. And so we'll go ahead and take that out. That's now 2/3. Limit as b tends to 3 from the left. I have 1 over root 1 minus, and our inverse sine's derivative has an x squared, so we have to make sure whatever appears here is all squared. So we'll make this into x over 3 quantity squared. And now we can go ahead and do a u substitution. U will be equal to x over 3. So du is 1/3 dx. Looks like I need that 1/3, so I'll go ahead and bring it back inside. Just leave this as a 2 outside. All right, so we'll go ahead and make that substitution. We got 2 limit as b tends to 3 from the left, x equals 0 to b, and we're looking at the 1/3 dx turns into a du. Look at 1 over root 1 minus u squared. And so we'll go ahead and integrate here. We get inverse sine of u from x equals 0 to b. And so we'll back substitute x in here. So this is x over 3. Sine inverse of x over 3. Evaluate from 0 to b. Almost there. We've got 2 limit as b tends to 3 from the left. And then we'll go ahead and evaluate here sine inverse of b over 3 minus sine inverse of 0. Sine inverse of 0 is 0. And so when we plug in 3, we get 1 in here. Inverse sine of 1, well, that's going to be pi halves, which gives us pi as our answer. All right, looking at this next one, determine whether the improper integral converges or diverges. At first glance, we might not even recognize this as an improper integral, but now that we know how to do them, we have to look out for domain issues. So looking at this guy here, I see that I have an issue at x equals 1. And so we have to keep that in mind, that we are going to have to look out for domain issues and sort of deal with those. So we're going to deal with a limit then, and we're going to be going to 1. Let's go ahead and replace it with a. And we do have to figure out then which direction to get it from. We're going from 1 to 2, which means we're looking at the right side of 1. We're going to come at 1 from the right. And so we'll go ahead and now we have an integral that we can work with. And it looks like we can probably do u substitution here again. This one we don't really have to mess with too much beforehand though. So we'll go ahead and let u equal x squared minus 1. So du will be 2x dx. We don't have a 2, so I'll go ahead and divide by 2. So there is my u substitution. And so we'll go ahead and make that swap. X dx becomes 1/2 du. I got 1 over root u. So that's the limit as, we'll go ahead and take that 1/2 out. 1/2. Limit as a tends to 1 from the right. Might want to keep that 1/2 in. We'll see in a sec. This is u to the negative 1/2 du. And since we've swapped for u, I want to make sure that my limits of integration still match up for x here. And so when we go to take our antiderivative, we increase the power by 1, divide by the new power, and it looks like we'll use up that 1/2 there. And so we have the limit as a tends to 1 from the right. Go ahead and plug our x back in. We got x squared minus 1 under a square root, evaluate from a to 2. So we have the limit as a tends to 1 from the right. And we'll have on the inside here root a squared minus 1 minus root 2 squared minus 1. All right, and we'll go ahead and Sorry, I just realized I did switch those. Upper one goes first. So 2 squared minus 1 minus root a squared minus 1. There we go. So we're looking at the limit as a tends to 1 from the right of root 3 minus root a squared minus 1. Plug in 1. Subtract 1, we get 0. And so our answer would just be root 3. So this guy converges as well. All right, so next up, again, it's going to be a case where it doesn't even necessarily look like it is an improper integral, but we do have to remember what the cotangent looks like. Remember, the cotangent has vertical asymptotes, again, every pi. But unlike tangent, we don't have that split, that origin intersection, and that split on either side of the y-axis. We actually have it on the y-axis. And so we're looking at this kind of thing. Right, we have pi here, 2 pi here. So looking at our integral here, we're going from pi halves to 5 pi fourths. So we have an issue at pi. So that's something we need to keep in mind to look for those issues. And so when we go to evaluate then, we're looking at evaluating both sides of that issue. So we'll have to split this into 2 different integrals. So pi halves to pi, and then finish it up with pi to 5 pi fourths. And so we'll have to introduce 2 limits. Limit as b approaches pi from, we're going from pi halves to pi, so that's from the left. And our other limit will then be approaching pi from the right. I'll go ahead and swap that for a. And then cotangent x dx in there. So we have our 2 limits. And we should know the integral of cotangent. Remember, that's one of the integrals that we should have memorized from a few sections ago. So that's going to be the natural log of the absolute value of sine of x. And so we'll go ahead and apply that to both integrals here. Oops, I put a -1 there, didn't I? That should be from the left. And that should be from the right. There we go. All right, so we got natural log of absolute value of sine of x divided from a to 5 pi fourths. So we got the limit as b tends to pi from the left. We have natural log of sine of b. Minus natural log of the sine of pi halves. Plus the limit as a tends to pi from the right, natural log of absolute value of the sine of 5 pi fourths minus natural log of the absolute value of the sine of a. So we'll go ahead and evaluate here. We've got pi, right? Sine of pi is going to be 0. So this is a problem. We got negative infinity. Sine of pi halves is 1, so we get 0 here. So we've got a problem. This limit doesn't exist. If this limit doesn't exist, then it does not matter. This guy diverges. And that's another crucial reason that we split this into 2 different limits, is because if we kind of shoved in the same limit, well, then there's a question of, can I somehow get this negative infinity to cancel out with something over here? And that's not going to work because of our definitions. To have a consistent system like this, we're going to have to make these decisions. You might look at the graph and see, well, I've got kind of the infinity here and the negative, but I got a positive infinity. Shouldn't those cancel? Infinities are weird like that. You can't necessarily just add infinity or subtract infinity from another infinity and get 0. And so based on our definitions and what we have to then follow for consistency's sake, this guy has to diverge. So probably a surprising result, maybe, for those of you who are looking at this. But that is what happens when we follow our definition. So that'll be our solution here, diverges. All right, so our last one here, we've got integral from 1 to 10. Again, first glance, might not think that this is improper, but we have x minus 2 in the denominator. So that's our issue. Issue at x equals 2. So we're going to have to, again, split this integral up. And I usually like to put the dx off to the side, so I'll put a 1 up there. So this will end up being two different integrals, 1 to 2. And then our other integral will finish it up 2 to 10. And so we'll have to introduce two different limits here. First, the limit as it's replacing 2 here, so b approaches 2. It's replacing an upper limit, so we'll go ahead and come at it from the left. So 1 to b. And then our other limit will be replacing the bottom there, so we'll go ahead and let that be a. A approaches 2 from the right. And on the plus side, with these improper integrals split this way, since we do have the same function, right? It is nice that we only have to do the antiderivative really once. So we'll have to go ahead and look at what is this integral in general. And is there a way to sort of solve through this, maybe without even using u substitution here? If we look at u equals x minus 2, then du is just dx. So really, we don't necessarily have to do much with this chain rule. So we'll go ahead and just write this as x minus 2 to the negative 1/3. And we'll just apply the power rule to it. So we got x minus 2. We add 1, so we get to the 2/3. We divide by 2/3, sorry, and that gives us 3/2. So that is our integral, so I don't need to write the dx anymore. Sorry about that. So x minus 2 to the 2/3 times 3/2. All right, and so that's what we'll go ahead and use in both of these situations. So feel free, if things are getting kind of cluttered and you don't want to keep your integral in line, again, since it's the same integral twice, we can go ahead and just sort of do it off to the side, shove it in for both here. And so since we're going to end up with a 3/2 for both, I'm going to go ahead and factor out the 3/2 out of everything. And so we'll get x minus 2 to the 2/3 evaluated from 1 to b. And then likewise, we'll get x minus 2 to the 2/3 evaluated from a to 10. So we get 3/2 times the limit as b approaches 2 from the left. And then we'll have, let's see, b minus 2 to the 2/3 minus 1 minus 2 to the 2/3 plus the limit as a tends to 2 from the right. And then in here we'll have 10 minus 2 to the 2/3 minus a minus 2 to the 2/3. Right? As b approaches 2, we can go ahead and plug that in, and we get 0 here. Same thing for this guy, 0 here, as a approaches 2. And so we'll have negative 1. So open up parentheses here, negative 1 to the 2/3 plus 8 to the 2/3. And so we'll go ahead and take the cube root of negative 1, we get negative 1. Square it, we get 1, but we still have this minus in front of it here. Plus, we get cube root of 8 is 2, square it, we get 4. So we get 3 halves times 3, so we get 9 halves. And so that'll be our final answer for that one. So it is important that we're mindful then of domain issues in our integrand so that we're able to find where we need to split our integral and how we need to make our limits. So that's it for improper integrals then, and that's going to be it for our unit on integration methods.